All right, chapter 4, here we go. So we're going to start out with 4.1, which is integer exponents. So you're going to be learning your exponent laws. The reason they have the word integer in here is for two reasons. One, we're going to be looking at positive and negative whole numbers. And then number two is that in chapter 7, we are going to use our exponent laws again, but we're going to be doing them with rational exponents. And so this is kind of like your warm up to like remember all of your exponent laws so that when we add fractions into things, your head doesn't explode. So first of all, everybody should know that an exponent is the upper part here. The whole thing is actually called a power or an exponential. So if you have 2 with an exponent of 5, we can read this as 2 to the 5th power, 2 to the exponent 5, 2 to the 5th. But what it means is that 2 is being multiplied by itself 5 times. And hopefully everybody's okay with plugging something like a 2 to the 5 into their calculator. Surely we've done some of these so far, but you will either plug it in as 2 to the exponent 5, or you could plug it in. Some people have a button that's like x to the y, and then you'd hit 5, but something along those lines. You do not have to type in 2 times itself 5 times. Okay, so let's get into our exponent laws. The first exponent law that we're going to talk about is the product rule, which is that when multiplying powers with the same base, what do you do to the exponents? Well, if you look at something like x squared times x cubed, we know that x squared is x times x, and x cubed is x times x times x. So now the brackets just mean multiply, so there's no difference between this bracket and another dot. So this is going to be x to the 5. So when we multiply powers of the same base, we can add the exponents because this is just saying there's, 5 x's all multiplying together. So product rule. When multiplying powers of the same base, you add the exponents. So if we have something like 3 to the 4 times 3 to the 7, it'd be 3 to the 4 plus 7, which would give you 3 to the 11. Now, they did numerical bases as well as algebraic bases for a couple reasons. One, to make you realize that you could plug this into your calculator to check. So if you plug in 3 to the 4 times 3 to the 7, you'd get the same answer as if you plugged in 3 to the 11. The only thing that bothers me is that sometimes they actually do plug into their calculator 3 to 11 and give you an answer, and sometimes they leave it as 3 to 11. So when you're looking at the back of the book, sometimes it'll say 3 to 11, or, now 3 to 11 is probably massive, but let's see what I get. 177,147, it would say something like or. Now for this one, I know it wouldn't. It would give you the 3 to the 11 as an answer, but just know that I would take either of those as an answer. This next one is 5 to the 3 times 5. And for this one, what they're trying to show you is that this is 5 to the 1. So if you are multiplying powers of the same base and you add the exponents, 5 cubed times 5 is the same as me saying 5 to the 4. And again, if you plugged in 5 to the 4 to your calculator, you get the same as 5 cubed times 5. And then I would take either one as an answer. I find it easier when it's variable bases just because there's no question of what to do. So if I have y cubed times y to the 8 times y squared, these are all the same base. So I get to add all of the exponents together, and I would get y to the 13. Then we amp it up a little bit. We add some more variables and we add some coefficients. So for this one, I've got 5 times y squared times negative 3 times y squared. I could write that as 5 times negative 3 times y squared times y to the 4. Because of the commutative property of multiplication, if you want to give it a fancy name, is that 3 times 2 times 1 is the same as 2 times 3 times 1. You're allowed to change the order of the way things are multiplied. So we're just going to multiply numbers with numbers and then same bases with same bases. So this is going to give me 5 times negative 3 is negative 15, and then y to the 2 plus 4 gives me y to the 6. All right, pause the video and see if you can give the next two a go. For this next one, I'm going to multiply the 7 by the 2, and I get 14. Then I'm doing p cubed times p to the 5, which again, you're adding the exponents. So you get p to the 8. And then this is q to the 1 times q squared, which would give me q to the 3. If you want to throw in more work for this, feel free. Some people do like that step in the middle. where they show, okay, I'm going to do 7 times 2. I'm going to do p cubed times p, whoops, that's not a p, times p to the 5. And then q to the 1 times q squared. And then we get 14 p to the 8 q to the 3. Right? Totally up to you what kind of work you want to show. And then what about this next one? This next one is a little bit of a trick. This one is trying to get you to think of, what do I do when the bases aren't the same? And so for this one, you would just say that it is not, like it's as far as it can go. I just checked the wording in the textbook and they said the product rule does not apply. Awesome. Okay, the next rule is the quotient rule. So the quotient rule is when dividing powers of the same base, you can subtract the exponents. So if you have x to the 5 over x squared, it would be x to the 5 minus 2, which gives you x cubed. And the reason why is that if I drew this out, x to the 5 is x times itself 5 times. And x squared is x times itself twice. And then you can do x divided by x is 1, x divided by x is 1, and I would be left with x cubed. So I always think of it as canceling out. These two x's are canceling out two of these x's to leave just 3 x's multiplying on the top. And I really do find when we get to starting to do negative exponents is that if you can visualize that, right, you can visualize this picture here, then the subtraction kind of just happens in your head and you know where your answer goes, which will make more sense when we get there. But try to have that picture when you're doing these. So for this one, I have x to the 12 over x to the 6. So now there's 6 x's that are going to take out 12 of the, or 6 of these from this 12. So you've got x to the 12 minus 6, which would leave you with x to the 6. If I put in some more variables here, it's bases with like bases with like bases. So x to the 4 minus 2, y to the 2 minus 1 would leave you with x squared, y to the 1, and we don't write the 1. If I throw in some coefficients, you divide the coefficients, so you get negative 12 divided by 4 is negative 3, and then we have b to the 6 minus 1, which would leave us with negative 3b to the 5. Be careful with these. There's not a lot of examples of these in the textbook, unfortunately, but I find as soon as a coefficient is involved, and this divides nicely, I find that if this had been a b squared, instead of getting b to the 4, which you should, people get b cubed because they divide. They're like, oh, negative 12 divided by 4 is 3, 6 divided by 2 is 3. But the rule for exponents is that it is subtraction, not division, and it throws people off all the time. All right, good luck with those.